Today we are talking about geomagnetically induced currents, GICs, in AC networks. As we can see here, we have the big sun, and here are sun eruptions or so-called solar flares. And they generate solar winds, and these solar winds are electrojets of thousands of amps DC. And those electrojets have an impact on the AC networks on our Earth, and this phenomena we will discuss during the next slides. In the past we have our standard power quality parameters in the AC grids, amplitude errors, phase errors, frequency and harmonics and supraharmonics. But the solar winds have an impact on the DC component in the AC networks. So only a few guys are looking at this DC component, and it's very hard to measure. In general, we are talking about a DC component when we see geomagnetically induced currents. But in fact, these currents have a very low frequency of 1 to 10 millihertz. But the most of the guys talk about DC components. The average magnitudes we can see are between 10 and 15 amps, and sometimes there are peaks of up to 100 amps for 1 or 2 minutes. GIC magnitudes of the order of several hundred amperes in neutrals have been observed in Finland and Sweden. More typical values of 10 to 15 amps were reported in the National Grid Company transmission system in England and Wales. In 1859, the biggest solar wind ever measured on Earth, strong currents shot through telegraph lines in some places, igniting the paper inserted in the telegraphs, to the horror of the technicians. Northern lights flashed in the sky far to the south between Cuba and Hawaii. Researchers estimate that this later so-called Carrington event was even 50% stronger than the magnetic storm in 1921. Because in 1921 power grids failed in Europe. It generated 10 times stronger currents in overhead lines. And then geomagnetic storm in March 1989, when it paralyzed the power grid in the Canadian province of Quebec, causing chaos as traffic control system, airport electrical system and district heating failed. 6 million people had no electricity for 9 hours. The last big event, 2003, their power grids failed in Sweden. There was a damage over 400 million euros. At the same time, the Japanese space agency JAXA lost contact with 2 of its satellites. If we have solar storms, solar flares, we have in our ionosphere fluctuating electrojets with millions of amps, and those currents have a magnetic field, of course, and we can see that here in the transmission line with the Earth's star point of those power transformers, we have a closed current loop, and that's why these magnetic fields of the electrojets can induce currents in these closed current loop. Here we have a figure with more details of those electrojets. Here we have an electrojet of 1 million amps and at an altitude of 120 kilometers, and the height is approximately 10 kilometers and the width is about 450 kilometers. And here you can see the power plant, and if you have transformers which are earthed at this site in this current loop. Then you have the closed current loop, we have talked about it, and then the magnetic field of those electrojets can induce GIC currents in the AC network. Yeah, these DC components can be very harmful for inductive devices, for example, power transformers. And here in this picture you can see this is a normal power transformer with the BH characteristic, and these are the magnetization currents of the core. And if we have saturation effects in one direction of the hysteresis curve, we have a deformation, we have totally other magnetization currents which flow into the core, and the transformer is going to behave like a nonlinear device, and this device is heated up and can cause some problems. Our instrument transformers are also inductive devices. Here we have an inductive current transformer, and here the hysteresis curve is shifted as well because of a DC component. The red one is shifted, and we can see here that we have a saturation. And if we have a look, here are some simulations with 100 milliamps, and this is a 0.2 current transformer, and it will lead to a bigger ratio error and a bigger phase displacement. And of course, if we get a bigger DC component, the ratio error grows and the phase displacement grows as well. Yeah, here we can see a transformer damage in 1998. This is Salem number 1 nuclear power plant in New Jersey, USA. And here the big power transformer burned. The geomagnetic superstorm on the 13th and 14th March 1989 caused the failure of many power transformers. They needed to be replaced, which was something the US electric power industry was not ready for. So there were big problems, and we can see here that the DC component heated up this power transformer. Yeah, besides the solar activity and the DC component, we can have DC components because of short distances between AC and DC lines, and of DC grids and their stray currents. For example, trains, they are powered with DC voltage. And of course we have then DC components in the AC grid. We have a half cycle saturation of transformers. This leads to harmonic distortion because the transformer is now a nonlinear device. We have transformer overheating, and of course an increase of reactive power losses, and everything leads to system instability, which results in the worst case to the blackout. Yeah, at DANISENS we produce current sensors with our special fluxgate technology, which are very famous for their accuracy. And we can see here in the diagram that we can measure very small currents. Yeah, here we have 1 milliamp, and we have a ratio error of 0.5%. So theoretically, we can measure those small DC components in AC grids. We can already do it in the low voltage grid with our existing transducers. Yeah, we can also do this setup with very big current transformers with a rated primary current of 5000 amps, and we can see here where we generate very small DC currents. We can measure, yeah, these are 10 milliamps and these are 50 milliamps, and we can measure easily, even with those big current transducers, DC components of 50 milliamps. But of course in the AC network we have some big AC amplitudes, and here we have a special test setup for a big current transducer with 800 amps RMS value at 50 Hertz, and we will generate a very small DC component with another current source, and we will try to detect this small component in this big 800 amps 50 Hertz signal. Yeah, we start here with 10 milliamps. You can see here the cursor of the recorder. And here we are at 10 milliamps. We can see the DC component, and we have, of course, some low pass filtering. And yeah, these are the values. And we have the big 800 amp 50 Hertz amplitude RMS value. This is the oscilloscope, unfortunately without a fitting trigger. And here the FFT analysis of the 800 amp amplitude at 50 Hertz, the biggest value, of course. And here we have the flexible FFT analysis, where we can see here the DC component. And yeah, we are now at 50 milliamps, and this is already, yeah, very accurate in my opinion. And yeah, it looks like that we can measure 50 milliamps very precisely. And now we go to the 100 milliamps, and yeah, I think it's very stable, the signal. And yeah, now we come to 1 amp. And here we can see the FFT analysis. So as a result, we can say that we can measure very small DC components even with a very big inner diameter and a big 50 Hertz amplitude. No problem. And now the test measurement for the DC component is ending. And thank you for your attention.